Sherwin from Newcastle, thermally and mechanically driven quantum turbulence in helium-2.
Hey, hi, I'm I better turn my Okay, so I'm Lucy Sherwin and I'm going to present just a short talk on thermally and mechanically driven quantum turbulence in helium-2. And this talk is based on a paper recently published in PRB, and it covers work done by myself in collaboration with Dr. Andrew Bagley, now of Glasgow University, and Professors Berengi and Sergeyev of Newcastle University. And just like a little advertising footnote, you'll see on the bottom here, I've got the logos of both Newcastle University and the JQC, and this is because we at Newcastle now work very closely with our colleagues at Durham, and we've come together to form a joint quantum centre. So, I'll just do a little bit of an introduction to some basics in helium-2, and I've just prepared a couple of illustrations to demonstrate the principles. So, on the right here, I've got a representation of the various states of helium. And the important part of this phase diagram is the region just above 2 Kelvin. And as the temperature passes beneath 2.17 Kelvin, we see the transition from a normal liquid helium to a mixture of normal helium and superfluid helium, or helium-2 as we call it. And as we approach this absolute zero, the superfluid component tends to dominate this mix. And so the illustration on the left here just is to highlight the blending effect between absolute zero and 2.17 Kelvin. Okay, so now I'm just going to highlight a few key differences between normal fluid and a superfluid. So a superfluid is inviscid, and its vorticity is constrained to lie on these quantized singularities. And so this illustration in the middle is just a representation of one of these quantized singularities, or a vortex as we call them. And so we can think of these, like Carlo said, as little tornadoes in the superfluid component around which the fluids circulate. And it's the movement and the interaction of these vortices which we study in our models. So, in contrast, the normal fluid is viscous, and we'd all be much more familiar with the normal fluid. It's more like water, and it's got a continuous vorticity field. Okay, so now I'm just going to do some basics of the maths that we use to model our superfluid world. And so we model our vortex lines as reconnecting space curves with fixed circulation, which move according to this equation here. And so in this equation, we've got Vs terms and we've got a Vn term. And the Vs terms just relate to the velocity of the superfluid component, while the Vn terms relate to the velocity of the normal fluid component. And then as well, the self-induced velocity of the vortex filament at the point S is given by the Bussard law, and I've just written this out in full at the bottom of the slide. So now if we look in a bit more detail at the normal fluid component, okay, so this can be modelled in different ways, and the two which I'm going to look at are a constant normal fluid component versus a turbulent normal fluid component. So a constant normal fluid component can be produced experimentally, for example, by applying a heat flux at one end of our system. And when we do this, the colder superfluid is drawn towards the heater and the normal warmer fluid is propelled away. And we make a couple of assumptions when we model this. One is that the heat flux is not great enough to create any turbulence in our normal fluid as it's propelled away. And the other is that the profile is constant, so that's to say that there's no interference by the boundaries, and so we're neglecting any channel profiles here. So if we now turn our attention to a turbulent normal fluid, then this can be produced experimentally either by stirring it or by using bellows to drive it. And so for computational ease, rather than using the Navier-Stokes equations, which would take an awful lot of computing power, we use a system called the KS flow, which is our shorthand for kinematic simulation. And by carefully selecting our parameters in this model, which is shown just here, we can force adherence to the Kolmogorov minus 5/3 spectrum in the normal fluid component. Okay, so I've prepared a short simulation movie. I'm afraid it is the same one that Carlo showed, so it might be a bit bored. And it's just to demonstrate how these superfluid vortices exist and interact within the helium-2. And the cube, like Carlo said, just represents our computational domain, and it does have periodic boundary conditions, which only means that as a vortex leaves the cube on the left, it's reintroduced on the right.
There was no forcing in the equation that you showed for the line for the superfluid. The equation ds by dt. Was there a forcing?
So,
well, you're going to say that the lines increase because you inject. That's what Carlo said. There's forcing.
Yeah, so this is a counterflow movie here. So we've got the normal fluid and the superfluid components here. And
well, something's forced. Where's the...
The normal fluid, actually.
Oh, there's no fluid. Okay.
Okay. And so at the start, you'll notice that there's just a few vortices, and I've illustrated what these are earlier, and we've looked at the equations which govern their motion. And this sparsity simply just represents the time when the system is getting established before reaching this pseudo-steady state, at which point the energy which is injected through the normal fluid is balanced by the dissipation due to reconnections. So hopefully my movie works. Okay, so the motion of the vortices themselves arises through their own self-induced velocity as well as them being advected by one another. And in addition, they're able to reconnect with one another due to collisions. And these resultant vortices after the collisions are a function of their states at the time, so that is, their orientation relative to each other and their direction of travel. And it is this tangle of vortices that is created and illustrated in this movie that we term superfluid turbulence. And then we will examine the characteristics of this vortex tangle and compare them with classical turbulence results and experimental superfluid observations.
Also, I was noticing early this morning. You seem to put in rings, but then the ring is disconnected. Is that the case?
So you mean at the initial kind of time?
Yeah, rings are not stable. They don't stay in rings for all time.
Yeah, so it always starts with these rings, and then as they reconnect with one another, these kind of reconnections are randomizing events which like distort them, if you will. Okay, so strictly speaking, this slide doesn't have anything to do with the work that we've actually carried out in Newcastle. This illustrates some experimental results by Maurer and Tabling in 1998 and Salor Roche and their group in 2010. Okay, so now I'm assuming from everybody having heard Carlo's talk that most, if not everyone, will be familiar with the concept of an energy cascade from large to small scales within a classical turbulent flow. And what these graphs represent is actual data from experiments using helium. And these two figures show the measured energy spectrum of established 3D isotropic turbulence. And figure 1 shows 3 distinct traces. So trace A, just at the top here, is measured at a temperature of 2.3 Kelvin, which is above the critical temperature where helium-2 is formed. And traces B and C are measured at 2.08 Kelvin and 1.4 Kelvin, and they are now in the helium-2 mix because we've gone beneath this 2.17 critical temperature. And figure 2 shows the energy spectrum at 4 different velocities and all at a temperature of 1.55 Kelvin. And at this temperature, the superfluid relative density is about 86% of the mix. So, some of you might have noticed that both of these figures are showing the minus 5/3 figure. And it is important to note that we're just seeing this minus 5/3 scaling where we would expect to see it. It's not over the entire range of the energy spectrum. And so this scaling derives analytically from Kolmogorov's theoretical work and is a well-established result in classical turbulence. And the fact that this is now mirrored in the quantum turbulence world, a very different system, is quite profound. So, if we now go back to our computational model, and first we set up thermally driven turbulence, so we've done this at 4 different counterflow velocities, and then we compute the energy spectrum. So this graph here on the left represents our results, and we don't see any minus 5/3 scaling here. What we see is a broad peak at the intermediate wave numbers, followed by a k to the -1 slope. So in other words, we're really not generating a lot of energy at the largest scales. So now if we look at the graph on the right, this shows our results when we've set up mechanically driven turbulence. And here we do see this minus 5/3 energy spectrum. And so it is important to note that this is in the superfluid component, and we are seeing this energy spectrum. And just a quick kind of note here, these dashed vertical lines that you see on both graphs, these just represent KL, which is the wave number corresponding to the average distance between vortices, or what we call the intervortex spacing. So, now we're going to do some further analysis of our vortex tangles that we produce. And to produce these images, we take a snapshot in time once we've achieved this steady state condition. And then turbulence, represented by the vortices, is manipulated by applying a Gaussian blur to the image, which helps us to visualize the vorticity and the interaction between the vortices. So it's important to note that both of these figures are plotted on the same scale, and that each box contains roughly the same cumulative length of vortex. So that is to say they have the same vortex line density. So on the left, we've got the visualization of the smooth vorticity when we've set up thermally driven turbulence. And on the right, we've got the smooth vorticity when we set up mechanically driven turbulence. And so it's quite apparent that the thermally driven turbulence is essentially featureless, and this is suggesting to us a more randomized orientation of the vortices. Whereas for the mechanically driven turbulence, we can see these regions of concentrated vorticity, or they're called vortical worms. And so this indicates to us more parallel vortices within this system. Okay, so now we're going to look at the angle the vortices present to one another when they are reconnecting. So we've plotted this angle theta for both thermally driven turbulence and mechanically driven turbulence. And we've chosen to look at this at 2 different temperatures, both of which would be experimentally achievable, 2.1 Kelvin and 1.9 Kelvin. So from the plots here, we can see that mechanically driven turbulence, which are these black lines, the peaks are around 0. And that's to say that the vortices are close to parallel when they're reconnecting. And so then if we look at the thermally driven turbulence, which is our red lines here, you can see that this time the peaks are much closer to pi. And that's to suggest that vortices are anti-parallel when they're reconnecting. So if we now take these results along with those on the previous slide, we can infer that in mechanically driven turbulence there must be bundles of parallel vortices which are not present in the thermally driven turbulence. So, as a final tool to understand what is happening here, we've chosen to look at the curvature of our vortices. And so, just a note on the conventions here, I'm going to speak about curvature, and this is in fact the inverse of the radius of curvature. So if I'm talking about high curvature, this is a small radius of curvature, and vice versa. And so when we plot this, we immediately notice that the mechanically driven turbulence, which is our black line, peaks at a relatively smaller curvature than the thermally driven turbulence, which is the red line here. So if I was to put this as simply as I could, if we were to visualize these tangles in our box, then the mechanically driven turbulence would look more like long spaghetti, and the thermally driven turbulence would be much more like spaghetti hoops.
Excuse me, the C bar is what? Is curvature?
Yeah, the mean
Is local
curvature.
curvature?
Yeah, the mean curvature.
Is the mean curvature?
Mm-hmm. Okay, so if I was to now sum all of this up, Well, I'd say that we've established that turbulence in superfluid helium can exhibit properties similar to that found in classical turbulence. But the establishment of these classical features is highly dependent on how we propagate our turbulence. So if the turbulence in the superfluid is driven by thermal drive, then it's quite different to ordinary viscous turbulence. But if the turbulence in the superfluid is mechanically driven, then we can see some features. For instance, we've seen the Kolmogorov energy spectrum. So the current working hypothesis here is that the presence of these longer, straighter bundles within the mechanically driven turbulence forms these large-scale motions that we need to create the Kolmogorov energy spectrum. Thank you.
Yes.
Am I right in thinking that you are assuming that in the thermally driven flow, the normal fluid is not turbulent?
Yes.
Whereas in practice, so real thermal, the induced flow of helium, it probably is turbulent, as we know both from experiment and from Carlo's stability calculations. So what you're dealing with here, I suspect, is a slightly artificial situation, which may not be directly comparable with a real physical situation.
Yeah, so we assumed that our heat flux was kind of not so much as to create turbulence as it's propelled away. So I suppose there's a point where it's going to cross over and, like you say, it's going to be turbulent. So we made that assumption on the other side of the line.
Between vertical, horizontal plates, the temperature gradient.
Yeah, I don't know experimentally if it's vertical, horizontal, but the idea is,
Makes a difference.
yeah,
It's a long channel.
long channel.
But it's thermal, so
So
with temperature.
You've got a heat flux at one end.
Usually a long channel, the temperature gradient, the longer channel.
Horizontal temperature gradient.
Well, maybe vertical, it doesn't matter.
Yes.
Actually, I have a curiosity. Maybe it's not technically direct to your talk, but is related to what Carlo and you said. How resilient is the scaling minus 5/3 to low temperature? How low can you go in terms of temperature to still get this 5/3?
In the experiments, I think the lowest temperature considered was 1.4 Kelvin, which corresponds to about 7% normal fluid only, so 93% superfluid. In the numerical simulations, the Kolmogorov scaling has been seen at T equals 0, so no friction, no normal fluid at all. So it's very resilient.
Is an ideal property.
It is an ideal property. It's
Yeah.
true at T equals 0.
But in answer to the question I raised about the forcing, of course, I should realize is because in mechanical forcing you do kinematic simulation of the normal fluid. So there is an implicit input of energy to the normal fluid. And then that normal fluid turbulence is simply stretching and convecting the vortex lines of the superfluid, which is why they increase in length. Yeah. Okay, thank you very much. And now we go.